Well, hello everyone. Good morning. Welcome to day 2 of NDC London 2021. My name is Enrico Campidoglio. This session is about writing tests with C#, just to check that everybody is on the same page. So I have lots of stuff to go through, so let's just jump right into it. Let me tell you just a little bit about myself. Let me see if I can actually change this slide. Yeah, there you go. As I said, my name is Enrico. I am a freelance programmer. This is me freelancing from home. I also do a fair bit of training, like online courses, workshops, and presentations like this one. All that done from home. No, who would have thought? Anyway, we're not here to talk about that. We are here to talk about writing tests using a library called AutoFixture. Now, if you've never heard about AutoFixture, let me just give you a quick intro. AutoFixture is an open source library for .NET, whose goal is to help you write better tests by auto-generating test data for you. Now, what that means, we're going to get into in a moment. But just to give you an overview, AutoFixture has been around for, I would say, around 10 years now. And it has been used quite a bit, I would say. It has seen some amount of usage. And in the interest of full disclosure, I am a contributor to the project, and I've been for a few years. And yeah, so this presentation is about how to use AutoFixture when you do TDD, to write dry tests. Now, let's start with a premise. And the premise is that tests that are small in size and that are expressive in the sense that they actually tell you what it is they are trying to test, that's a good thing. We want that in our tests. Do we all agree on that premise? I'm going to take that as a yes.
Yes.
Good. Perfect. How are we going to do that? Well, we're going to leverage 3 unit testing patterns. And these are well-documented patterns that are part of the book XUnit patterns that's been around for many years. We're going to use 3 of these patterns, but we're not going to implement them ourselves. We are going to use a library that implements those patterns for us and leverage it that way. And if you can guess, that library is AutoFixture. Let's talk about this word right here. Actually, let's focus on, everybody agrees on what auto means, that's automatic, but what is a fixture? So let's focus a bit on this. Let's talk about what a fixture is, because it's kind of important in this context. Now, when you write a test, you have a system that you are trying to test. And in the case of unit tests, that would be a class. Now, in order to test a system, you have to put it into some kind of context. Well, that context in which you put your system under test in order to verify its behavior, that's the fixture. And how does a fixture look like? Well, if you've written at least one unit test in your life, you know how a fixture looks like. You invoke methods or set properties on your system under test. You generate values that you pass into the methods as test arguments. And ideally, a test should contain a pretty small amount of this context, because ideally in a unit test, you should verify one thing. And in a perfect world, that one thing will require a minimal amount of context. However, reality is much different than that. We all know that these contexts, they grow in size. And you don't need just, maybe for your particular scenario, you need one value, but because of the nature of the system, you have to create a lot more stuff in order to be able to test it at all. And that involves creating entire object graphs, coming up with more values. Sometimes you don't know what to pass in, so you pass null. And that's how our tests usually look like. A lot of setup code for what is actually very little behavior to verify. But we have another problem. So it's not just, it's like it's not enough to have big fixture. Well, another problem is that for every time you invoke your system on the test, by passing arguments or by actually invoking its API, you are creating coupling onto it. And that we know that coupling, what it means is that it's going to be harder to change. Now, imagine not having one test with this scenario, but having the same thing be repeated for every test. Of course, every test is going to need a fixture. And in most of the cases, if it's the same system you are testing, you're going to have to create pretty much the same amount of context for every test. So we have duplicated setup code everywhere. Maybe sometime you change something in particular test. For example, you change this value to foo, or maybe you pass 42 instead of 12. And what happens is it starts small, but it grows really big. And you know, that's no good. So how are we going to solve that problem? Well, let's take a look at how a test is built. You all know that that setup that we've been talking about in the formal terminology, that's called the arrange phase. And that's where we set up our fixture. Now that's usually pretty big. The second part of a test is act. The third part is assert. Now you see the proportions here. Arrange is a lot bigger than the other two. Now what we want to do with AutoFixture is reduce the size of this arrange so that it contains the minimal amount of context that we need for a particular scenario. So in other words, if the scenario ideally would require a certain size of context, we want a fixture to match that size. We don't want to create anything more than what is necessary. In other words, we want to reduce the amount of calls that we make onto our system under test, thus reducing coupling and duplication. Because you know that fewer explicit calls you make onto your system under test, the easier it's going to be to change. So let's switch gear and talk about these 3 unit testing patterns. Now that we have talked about what the problem is, let's talk about how we are going to attack it. The first unit testing pattern that we're going to use is called anonymous data. Now, what's anonymous data? Well, it's any input value that exercises the code path under test. Now, let's unpack it. Imagine a method like this. It takes an input value, that's an integer, and it has exactly one line of code that checks whether the value is positive or not. Now, it doesn't really matter what number you pass into this function. That line is always going to be run. So you say that that value can be anonymous. As long as it exercises that line, it doesn't really matter if that's a 2 or a 42. So we can leave it anonymous. The second unit test pattern is called equivalence sets. And now this is sounding more exotic by the minute. So what is it? Given that we have anonymous values that we can pass in, the set of those values that exercises the same code path through the code is said to be an equivalent set. Now, again, let's take an example. Imagine a slightly more complex function where you have an input value and you have two branches that execute based on what that value is. Now, if I invoke this method with the values 4 and 9, those values are bigger than 3, and they will execute that line of code. If I invoke this method with 0 and 2, those values are less than 3. That means they will execute the other branch. Now, 4 and 9 and 0 and 2, those are equivalent sets. Those, from the point of view of the test, it doesn't really matter if it's one or the other, as long as it exercises the same line of code. So those are equivalent. The third and final unit testing pattern is called the test data builder, that actually, no pun intended, builds upon the other two. Now, if you remember what we just said, we said that we can leave some values anonymous when we write tests, as long as they exercise the code that we are interested in verifying. So if we can leave them anonymous, it means that we can actually delegate the responsibility of coming up with those values to an external party. And that external party is the test data builder. So a test data builder is a factory. We all love factories that creates values used to test a specific code path. So, given this method, any small positive number that we pass in is going to be enough to exercise all the possible code paths. This means that our test data builder, the values that it will come up with are enough to cover the vast majority of the code path that we have in our code bases. So the usual 80-20 rule says that a test data builder can cover 80% of the cases just with its default values that it comes up with. For example, a string is going to be a string, an integer is going to be a small positive integer, a Boolean can be either true or false. So given these defaults, we can cover 80% of the code paths. However, there is a remaining 20% in which we actually need the value to be of a specific kind. And for those cases, our test data builder will need to have some way to let us customize the test data that it produces. Now that we have gone through the theory, let's talk about how we're going to demonstrate it. Now, in this talk, I'm going to implement Conway's game of life, which is C# in a test-driven manner, using AutoFixture as our test data builder. Now, if you are familiar with the Conway's game of life, that's good. If you're not, here is a quick intro. Game of life is a logic game invented by Conway that consists of a grid of cells, and each cell can have either one of two states. It can either be alive or it can be dead. Now, this entire grid of cells is going to be refreshed, and that means that you basically recalculate the value for all those cells based on 4 specific rules. And all those 4 rules have to do with the state of any given cell's neighbors. Now, as you refresh this grid, that's called a generation. Any particular snapshot of cells is a generation. So when you calculate a new generation based on those rules, some cells will come alive, some other cells will be dead. And that creates patterns for every time you refresh this grid. And that's kind of interesting because based on what the start pattern is, every time you refresh, some patterns are perpetual, they will go on forever. Other patterns will eventually lead to all the cells being dead, all based on what the start pattern is. Pretty interesting stuff. Now, we're not going to implement all 4 of these rules, otherwise we'll be here until tomorrow. We're going to implement just one of the 4 rules. And this rule is called the rule of underpopulation, which goes like this. A cell that's alive, but that has fewer than 2 live neighbors, is going to die in the next generation due to underpopulation. So that's the rule we're going to implement. We're going to implement it in C# in a test-driven manner. So without further ado, let's TDD. Okay, let's see if I can, there you go, switch to Visual Studio Code. All right, so what I have here is, Visual Studio Code. I have a sample project on my left, which might be your right. I'm not really sure. Anyway, on one side are the tests that we're going to write. And on the opposite side, we have the production code. So I have a little starting point here where I have created a test class. Now, notice how I'm writing this test class. Usually, maybe if you're used to having your tests in a class that has the same name as the class you're testing plus the test or test suffix. I also used to do that. But a few years ago, I stumbled upon a different style of writing unit tests that's called BDD style testing, where BDD is behavior-driven development. Now, BDD style testing means that instead of focusing on the implementation, you are rather focusing on the behavior that you are implementing. And that all starts with naming your tests. So instead of having a test class for every production code class, I have a test class for each scenario. And in this case, the scenario is when I calculate a new generation. This is what I want to test, which is basically, as we just said, the essence of the game of life. It's refreshing this grid of cells. It's producing new generations. And that really helps me focus on the functionality. Now, we said we're going to do it test-driven. So here we are with a blank sheet, and we have to write the first test. Now, we all know that's the hardest part of writing TDD. What really helps is to think of what is the simplest, most trivial piece of functionality that my code has to accomplish. Now, in this case, we have a grid of cells. So if I pass into my generation class, if I pass in a grid of cells into that, and I ask it to calculate a new grid, I expect to get back a new grid. So a first test could be something along the lines of when calculating a new generation, it should return a generation containing cells. That's the easiest thing I can come up with when if I were to implement a game of life algorithm. Now, we mentioned at the beginning of this talk that every test has 3 sections: the arrange phase, the act, and the assert. Now, let's start by writing this test without AutoFixture, without using those unit test patterns. Let's write it the usual way. And after we are done, let's take a look and let's see how we can refactor the tests to become drier and to become smaller and more expressive. So let's start by writing it a regular way. The arrange phase could look something like that. We have a generation class which contains a list of cells. And these cells, they have coordinates in the X and Y, along the X and Y axis. Now, as you, and by the way, our system on the test, which I called SUT, system on the test, it consists of a grid, whose responsibility is to calculate a new generation of cells. Now, if you notice here, it doesn't really matter what these values are for the purpose of our test. They could be anything. They're not even neighbors. We haven't really specified the size of the grid either. We're just passing some random numbers because from the point of view of this test, we are just interested in getting back a generation of cells. It doesn't really matter what their coordinates are. So these values are anonymous, just a hint for later. So this being TDD, of course, we have a compilation error because none of these classes that we have mentioned actually exist yet. So let's go ahead and implement those. So let's start with a class called a generation, and which is going to have a constructor which accepts a list of cell objects. So let me just quickly implement that. So as you see here, I just have a generation that takes an enumerable of cell. And of course, the cell class doesn't exist either. So let's go ahead and implement that. Cell. Ooh. Let's see. Public. Actually, I like it to be indented. Class cell. And the cell class is going to have a constructor which accepts two numbers, which are the coordinate. And let's put two properties for good measure. So far, so good. Pretty simple stuff. Now, the third thing we need to create is the actual grid, which is our system on the test. So let's put it where I'm putting all the classes in the same file. Of course, you're not going to do that in production code. Well, actually, when doing TDD, it's pretty convenient to have all the code in the same file to begin with, just because it gives you less friction. And then when you have made the test pass, you know, the famous Red-Green-Refactor, first make the test fail, then make it pass, and then refactor. In the refactor phase, that's where you can move out the classes to different files. So public class, let's call it grid. And which should be good. So let's try to compile. Now I'm using Visual Studio Code with OmniSharp to give me the IntelliSense. So yeah, the compilation has succeeded. However, the squiggly lines are still here. And that's because OmniSharp hasn't really caught up yet. But it will eventually, so let's proceed. The second part of the test is going to be the act. That's when we actually invoke our refresh method. And here we go. So we are invoking a method called refresh on our system on the test, where we passing the generation that we have created. And we expect to get back a new generation where hopefully the cells are still the same. Of course, the refresh method doesn't exist, so let's go ahead and implement it. And so remember that when you're doing TDD, you have to write the least amount of code possible to make the test pass. And in this case, I'm just going to create a stub of a refresh method that takes a generation and returns a different generation. But in this case, I'm just going to return null, because our goal is to just have this compile. So let's go ahead and do that. Perfect. Compiling is the first green in the Red-Green-Refactor cycle. The third phase is the assert. So let's verify that what did our test say? It should return a generation containing cells. Okay, so we just need to verify that this generation is not empty. So here is how we express it. We say that the next generation should not be empty. Now, if this looks new to you, this is another library that I really like called Fluent Assertions. So instead of writing assert that or assert not empty, like the assertion libraries built into XUnit or NUnit do, I use a third-party library that's just dedicated to giving me assertion methods. And those assertion methods are implemented as extension methods, which means I can append them instead of having them up front. What this allows me to do is I can express this as a sentence, thus making it more expressive. However, in this case, we see that this is not compiling because the notBeEmpty extension method extends IEnumerable. So in this case, we are assuming that the next generation, or rather the generation class, is in of itself a list of cells, an IEnumerable of cells, which is it's actually what it is. So it's not a bad idea to, in this case, go ahead and implement IEnumerable of cell on the generation itself, because if you think about it, a generation is a list of cells. So the implementation is also rather trivial. So let's just go ahead and implement the get enumerator methods, where you just iterate through the list of cells that's in the generation. Now let's go ahead and compile. Let's see if this is happy now. Yeah, looks good. Now let's finally run the test after all this. Okay, so the test failed, and not only the test, but my microphone also failed together with the test. So that was kind of catastrophic. Let's hope that it doesn't happen next time I run my tests. Otherwise, it's going to be really spooky. So not only does it have to fail, but it also has to fail in the expected way. And the expected way is we expected the next generation not to be empty, but we found null. So that's exactly what we wanted. So now the next step is implement the least amount of code that we can write to make this test pass. Now, what is the least amount of code we can write? Now, of course, the test just asks for a generation, a list of cells. So let's give it an array containing one cell. And that cell doesn't really, it doesn't even have to have any actual cells in it. Because let's see, generations, yeah. Now it's the resharp, the OmniSharp that's going crazy. Let's try to compile and see what happens. To demo generation. Why not? It is an IEnumerable of cell, isn't it? New, of course, yeah. We pass it a new generation, where we pass an array of cells that contains just one item, and that cell doesn't really have to actually be an actual cell. So let's compile. Perfect. Let's run the test. Let's see if it's still passing. Perfect. Now we have the green. So red, we did that. Green, we have it now. Refactoring we'll do later. Let's proceed to the next test. Next test is, now that we know that our method actually returns a generation with some cells, now we need to verify that if we send in a certain amount of cells, what we want to get back is the same amount. So the test here now becomes, the next step is it should return the same number of cells. In other words, this refresh method shouldn't add nor remove any cells. Ooh. There you go. So how is the arrange phase going to be in this case? Well, as I told you before, when you are testing the same scenario with different assertions, we are going to be creating the same arrange. So these arrange phases are going to look a lot alike. They're going to be duplicated. So in this case, we're still going to have to create a generation. We're still going to need to pass a list of cells. In this case, let's just pass 3 instead of 2, just to make something new. Again, the numbers of the coordinates don't really matter. The act, of course, is also going to be the same. We send in this generation, we refresh it, we get back a new generation, and this time the assert is going to be different, because now we're going to verify that if I pass in 3 cells, I want to get back exactly 3 cells. All good. Let's run this test and see what happens. Failed, perfect. Microphone is still on, also good. How does it fail? Let's take a look. We expected the next generation to contain 3 items, but we found 1, which is exactly what our implementation is doing. So again, let's make this test pass now. What is the least amount of code I can write to make the test pass? Well, of course, I could write 3 here or 4, but then we wouldn't be moving the implementation forward. So another trick with TDD is that, of course, you are playing devil's advocate all the time by saying, what is the least amount of code I can write? But you can't just stand still on the same place. You need to actually drive the implementation forward. So in this case, just changing that number wouldn't get us anywhere. What we need to do instead is go from a constant value, like in this case, to a variable. So what can we return? Well, the simplest thing we can do is that we return the exact same generation that we get in. So we went from hard coding an array with 1 item to, which is a constant, to a variable. This should be the least amount of code that we can write to make this test pass. And the other one, of course. And indeed, we have now 2 passing tests. Now, the third and final, the rule of 3, test that we have to write is the actual underpopulation rule. So now we're just setting up the basic infrastructure to have a grid of cells. Now let's actually implement this underpopulation rule. If you remember, the rule says that if there is an alive cell that has fewer than 2, or it doesn't have any neighbors that are also alive, it's going to die in the next generation due to underpopulation. So in this case, the arrange is going to be slightly different than we had, because in this case, we actually do care about the number of cells and the state of those cells. So let's see how this arrange looks like. So instead of just creating a bunch of cells, in this case, we create just 1 cell, which is the one that we want to die from one generation to the other. And that, let's call it the solitary cell, because it doesn't have any neighbors. Another new piece of information that we need to bake in is the state of the cell. So now the coordinates still don't matter, but in this case, we actually want the cell to have a state, which is either alive or dead. So it's a Boolean. And we want it to be alive to begin with. Then we pass in the usual list of cells to the generation. In this case, we pass in just that one. We create our grid, which is our system on the test. And the rest, you know the drill. So In this case, we actually don't care about the value of that we get back. Instead, let's just verify. Ooh. Let's see. Let's just verify that this cell that we have passed in, its alive property should be false. So we are just passing in a cell with a certain state, with no neighbors. We pass it in, we say refresh, and then we check that that cell now is dead. Of course, this doesn't compile because we have introduced a new constructor parameter. So let's go ahead and add that to the cell class, which is over here. So let's add alive. Let's also add a property. Now we do it as a readable and writable property because you can't change the coordinates of a cell, but you can change its state. I know maybe it shouldn't have be done through a property, but for the sake of this exercise, let's make this a mutable state. And let's assign it from the constructor. Okay. Now let's see if we are good. What do you think happens now? Ooh, compilation error. Why? I can almost hear you say that, hey, you just added a new constructor parameter, but all your existing tests are passing just 2 arguments. So now we have just broken our existing tests. And this is a very concrete proof of the coupling that I was talking about earlier. For every call you make to your system on the test, in every single one of these arrange phases, you are creating your tests are coupling themselves to your implementation, which inhibits your ability to evolve it and to refactor it. So in this case, we need to move this implementation forward, or we just broke our existing tests. Now, in this case, there are only 2 of them, but imagine having a library of hundreds, if not thousands of tests. And by making a change in your API, you're suddenly breaking all of them. And who wants to go through thousands of tests and fix them? So what happens in most cases, you just don't refactor. Your tests are now a burden. I know it sounds really, really dark, but in this case, we can actually get out of it by leveraging a feature in the C# language called default parameters, where you can say that, okay, I'm just going to assume that when I create a new cell, if I don't pass any state, that cell is going to be dead. And just by doing this move, I now have fixed my compilation errors. But you see that this is a lucky situation. You're not always able to do this. So now the test starts compiling again. And let's run the test. We need to see it fail. Yeah, 2 passed, 1 failed. Why is it failing? The expected solitary cell .alive to be false, but we got it true. In other words, it hasn't changed its state. Perfect. Now, what is the least amount of code I can write to make this test pass? Now, the code I'm about to write is the most naive, trivial implementation, which is, of course, not what the final implementation should look like. But in our case, we're not interested in producing the perfect implementation of the game of life. We are focusing on the tests. So let's do the most naive, embarrassing implementation ever and say that given the seed, the generation that I pass in, I'm going to get the first element out of it, and I'm going to set the alive property to false. How is that? I can almost hear the screams of the people. What are you doing? I know. But this is not, of course, you're going to, ideally, you write more tests, you evolve the implementation, you refactor this away. But we're going to stop here for now. Let's just forget about that implementation. Perfect, all 3 tests are passing. Now we are in a state where we can forget about this implementation for now and just look at our tests. Now you see the problem. I've already talked about some of the problems that I mentioned in the beginning. We have some, we have duplication, we have coupling, and we have also interesting things like, what are these numbers? Are they meaningful? What happens if I change one of them? So there are lots of these questions. So how can we solve the problem? We can solve it by leveraging a test data builder like AutoFixture. Now let's start refactoring those tests. And now I can almost hear you asking, hey, but if you refactor your tests, how do you know that you haven't broken anything? Well, let me tell you this. When you have tests and you have your production code, you can only ever refactor one or the other, never both at the same time. So in this case, I'm not touching the implementation. The implementation stays the same. We are refactoring the tests. So by not touching the implementation, we know that we haven't broken any test. So let's change this arrange and let's use a test data builder like AutoFixture. So AutoFixture starts with an object called a fixture, like of course it says it right on the name, a fixture class. And the fixture class has a method called create, which you can use to actually ask it to produce a value for us. So in our case, we're going to say fixture.create. What type do you want to create? I want to create a generation. And I can also ask it to create my system under test. So let's create a grid. So let's remove this. So now instead of manually invoking all the constructor and coming up with the values myself, I just delegated all of that to the test data builder and ask it, just give me an instance of this with good default values. Let's see if it still passes the test. Yeah, it does. Perfect. Now, in this case, we said that what happens if I change this number to a different one? For example, what happens if I add another cell and pass in some random values? Of course, if I change this value to 4, that should still, oh, I forgot a comma there. The test should still pass because it doesn't really matter how many there are as long as that's the same number that's coming out. So let's use AutoFixture to create all of this setup for us. We're basically doing the same thing. Oh. There you go. So create a fixture, we ask it to create a generation, and we ask it to create a grid, just like we did before. Let's get rid of this stuff. And let's see if the test is still passing. What do you think? No. Test has failed. Let's see why. I mean, it shouldn't, right? So expected the next generation to contain 4 items. Yeah, we said 4, but we got 3. So what is this? Remember, AutoFixture works by using reflection. So what it does is that when I ask it to create a generation, it's going to look at its constructor and see that, aha, the generation requires an enumerable of cell. And of course, the cell object is going to have X and Y and the alive property. So those are going to get just some random positive numbers. But when AutoFixture is tasked with creating a list of anything, if you are not specific and tell how many items the list should have, it's going to give you 3. Why 3? Because it's a good, sane default. So in this case, we get 3, not 4, because AutoFixture is using its default. But if you look at our test, does it really matter for a test how many there are? No, it doesn't, as long as they are the same number. So instead of hard coding the value, we can say have the same count as the seed. So by using a test data builder, in this case, we have made our test less hard-coded, more generic, and in that way also more expressive. Because now it doesn't really matter how many there are, we're just checking that they have the same amount. So does this test pass? Yes, it does. Now, the final test is a little bit more complicated because now we actually do care about the number of cells, and we also care about the state. So how can we write this? Now, remember the 80-20 rule. Up until now, we just leveraged the default values that AutoFixture comes up with. So they cover 80% of the cases. In this case, we're going to use the customization API that AutoFixture has in order to actually go in and tell it, okay, I want you to create exactly one cell, and that cell needs to be alone and it needs to be alive. So we start by using the fixture, as always. However, now we need to tell AutoFixture how it should create certain types of objects. So we say customize. Customize what type? Well, we want to customize the cell type. And this method takes a lambda where you say create and then you say with, and then you need to specify, okay, which property do you want to set to a particular value? Well, I want to set the alive property. What value do you want to give it? I want to give it true. So now I'm telling AutoFixture, customize for every time you want for this particular test. The fixture is always for one test only. For this particular test, when AutoFixture has to create a cell, it's going to create it with the alive property set to true. Now, the second part of the customization is we want a list of cells to contain just one item, not 3, not 4, not any number other than 1. So it's another customization we need to use. Customize single, let's go, what is it called? Single, actually, I don't remember the name, let me see. Single element sequence, there you go. So fixture, customize, new single element sequence of cell. I'm just going to explain real quick what this is. So this is a customization that's pre-packaged. And what this says, it tells AutoFixture that every time you have to create a sequence of cells, that means an enumerable of cells, it's going to give it a single element. So now that we have customized AutoFixture and told it what to do for those types, then we can just create our generation and our grid as usual. So let's get rid of that. Now we have another problem. You see, now we no longer have access to the solitary cell variable because it's being created behind the curtains by AutoFixture as part of the arrange phase. We don't actually have a reference to that value. But that's also something that we can easily solve, because if we instead check the return value of our method, the next generation, then we can say next generation dot single, and in this case we do know for a fact that the next generation is going to contain a single element because we told AutoFixture to do it. So it's perfectly fine to go ahead and build on those assumptions because those are part of the arrange phase. So we say that the single cell in the next generation should be alive, should be false. Let's see if this passes. Perfect. So now we have refactored the tests. They are not only more expressive, they're smaller, but they are also decoupled from the implementation. What does this mean? It means that if I want to go into the implementation and improve it somehow, for example, I no longer need this. And what about this constructor? What if instead of having an enumerable of cell, I want to allow the caller to specify any number of cell objects by using params? So for example, I can say params cell cells like that. Now, making it more flexible. Now I can make those changes and I can still run my tests and verify that I haven't broken anything. So this is a really powerful, those three patterns and a AutoFixture as an implementation of those three unit testing patterns gives us the freedom to write tests that are readable, expressive, and that are decoupled from our implementation. The only, of course, we're going to have be coupled at least a certain amount because we need to actually invoke our system on the test. But we are free to refactor our code and take advantage of the safety net that are our tests. Pretty powerful stuff. So now I have a few minutes, so let me go back to the slides just to wrap this up. Now, if we're going to remember just one thing from this presentation, let's make it three things. The first one is do not hard code values into your tests because they confuse the picture. They create questions that are not really relevant. The test should be readable as is, and they should communicate what it is that they're trying to verify. The second takeaway is try to minimize the amount of coupling that your tests have on your system on the test, because that will give you the freedom to refactor. And having the freedom to refactor means easier maintenance of your code base, which is the ultimate goal that we strive for every day as programmers. With that, I just want to give you a few pointers. So there is an AutoFixture tag on Stack Overflow where myself and a few others from the AutoFixture team are watching and trying to answer questions as they come up. And AutoFixture itself, of course, is open source and it's on GitHub. So if you have any issues or questions, you can post them over there. As for myself, if you liked what you've seen today, I just wanted to give you a pointer to my Pluralsight courses. So I have a few Pluralsight courses out. My latest one is about GitHub Actions. And there is the link if you want to check those out. I would really appreciate that. And with that, I want to say thank you for watching this presentation. And I'll stick around the chat for at least the rest of today. So if you want to ping me there and ask me questions, I'll be very happy to answer if I can. And yeah, enjoy the rest of your conference. Thank you.